Alright, in this video we're going to talk about triple products. So a triple product is a product that involves three vectors. So it could be cross or dot products of the involved vectors. Okay, we list two properties. The first one is a scalar triple product. So it's a triple product whose final result is a scalar. So A dot B cross C, so this is a vector, this is a vector, so the resulting thing is a scalar, is equal to B dot C cross A, which is equals to C dot A cross B. This gives the volume of a parallel piped whose edges are A, B, and C. Parallel piped is a bit like a cuboid, but where the edges do not make necessarily 90 degrees. So if this is vector A and this is vector B, just one moment, choose another direction. This is vector B, then so that's still vector B. This is vector A. If this is vector C, then this could be parallel piped. Okay, so this is vector A, this is vector B, this is vector C. Then the volume of this thing here is going to be given by the magnitude of that. So so this thing is just a number, so the magnitude is just saying the number is going to be like obviously the volume is a positive number, so if you take the positive of that, then that's going to give you the volume of the parallel piped. So also the this scalar product here, A dot B cross C, can simply be found by doing the determinant of this matrix here, where you have got A components of A in the first row, components of B and components of C. We're actually going to prove this in the examples that follow. Then for a vector product, okay, of three vectors, triple vector product, so A cross B cross C is ambiguous, so we need to put brackets either here or there, because whichever of the two you do first makes a difference in the final result. If you do B cross C first and then cross that with A, or if you do A cross B then cross that with C, then it gives us two different outcomes. So this one is given by this formula here, and this one is given by that formula there. Alright, so let's look at some examples. Alright, in the example number 1, we have three vectors. So A, we got B, we have got C. In part A, want to find C dot A cross B. In part 2, A dot B dot C. In part 3, want to find a unit vector perpendicular to both A and B. In part B, we want to show that A, B, and C are sides of a triangle. Okay, so let's have a go So in the first instance we need C dot A cross B. So first we're going to work out the quantity in the brackets, so in the style of board mass. Okay, so A is 5J minus 3, so there's no K. So minus 3 here, 5 here, K, the Z component is 0. B, we have got minus 4, 3, 1. So minus 4, 3, 1. If we do this along the third column, going to have K into minus 3, 5, minus 4, 3 plus IJ minus 3, 5. So that's going to be minus 9 plus 20. So 20 minus 9 is 11. Then here we are going to have 5I minus 3J. So that's going to be A cross B. If we put these in order, it's going to be 5 minus 3, 11. And then we need to do cross dot product with C. I'm going to use a column vector notation now. C is 1, 2, minus 1. 1, 2 minus 1 dot 5 minus 3, 11. This is going to be 5, which is 1 times 5, minus 6, 2 times 3, minus 11. So this is 5 minus 6 is minus 1, so it's going to be minus 12. Okay. Then part 2, we have got A dot B dot B dot C. Okay, now look at this. A dot B gives us a scalar. Okay, so this is a scalar here. B dot C is also a scalar. Okay. Now, so what is happening here? This thing is suggesting we dot a scalar with a scalar. But that doesn't make sense. Okay. We only do dot product between vectors. So we have got to conclude that this thing here does not make any sense. Does not make sense, or if you like, this is impossible. Part 3, want a unit vector perpendicular to both A and B. So first of all, we need to find a vector perpendicular to A and B from the previous video, we've already mentioned that the cross product of A and B is going to be perpendicular to both of them. So that means the unit vector we're looking for is going to be in the direction of this vector here. Now, the unit vector in any direction of a vector, so once we've determined the direction of the vector, of which in this case it's this one, okay, then the unit vector is simply going to be, if I denote it u, or maybe let me denote it v, okay. So unit vector is going to be the vector v divided by the magnitude of the same vector. So in this case, v is this vector here, 5 minus 3, 11. So 5 minus 3, 11. Then we're going to divide that by the magnitude of the same vector. 5 minus 3, 11. So 5 minus 3, 11 divided by the square root of 5 squared, negative 3 squared, plus 11 squared. So that's going to be 25 plus 9 plus 121. 25 plus 9 plus 121. That's 155. So it's divided by 155. So that's going to be the unit vector. It's divided by the square root of that. We can either leave it like this, or we can write it as 5 over square root 155 minus 3 over square root 155, 11 over square root 155. Okay. No, alternatively 1 over square root 155 into this vector. Okay, so this is going to be a vector of magnitude 1. Next question, B. Show that A, B, and C are sides of a triangle. So, if you have a triangle like this, if you have a triangle like this, and this is vector A, this is vector B, this is vector C, then here what it means is that C is equal to A plus B. Well, or alternatively, A is equal to C minus B. Okay, so if we're given 3 vectors, they form sides of a triangle if they satisfy this identity here. So if we can show that the sum of 2 of them is a third triangle, then the 3 vectors form a triangle. The sum of 2 of them is equal to the third one, okay. Then we have shown that they form the sides of a triangle. So these are three vectors we have here. A is 5j minus 3. A is 5j minus 3i. B is k plus 3j minus 4i. K plus 3j minus 4i. For I, and C there we have C. I plus 2j minus k. So I plus 2j minus k. So you can show that if you add two of them, you get the third. Then we have shown that. So there is a bit of trial and error here. Let's do a plus b. So a plus b, if we take the i's, we have got minus 4i minus, so that's going to be minus 7i. The j's got 5 and 3, going to be 8j, and then just that k, and this is not equal to c. So let's do a plus c, and then if that doesn't work, then the final one is b plus c. So a plus c, here the i's, minus 3 plus 1 is minus 2i. The j's are going to add up to 7j, then minus k. This is not equal to, we're doing a and c. Okay, so if this is showing that we've got a triangle, it should be equal to b. It is not. Then finally we do b plus c. So b plus c, if you look at the i's, we got minus 4 plus 1, which is minus 3i. If you look at the j's, we got 3 plus 2, which is 5j. Look at the k's, got k minus k, that's 5j minus 3, and indeed this is equal to a. Okay, and so these vectors form a triangle. Okay, let's go to the next example. Okay, in this example we want to find the work done in moving an object along the straight line from minus 21 to 39 under the influence of the force 7i minus 2j. Right, so for starters, work done, the formula for work done is equal to force dot the displacement vector. So let's call it delta r. Okay, so the force is given here. We need to work out this one. So delta r is going to be, so we're moving this thing from minus 21 to, it's a straight line 39. So we need to express that as a vector. So it's going to be, the x component is going to be 3 minus negative 2. 3 minus negative 2. The y component is going to be 9 minus 1. So it's 5i plus 8j. The force field is 7i minus 2j. 7i minus 2j. So the work done is going to be F dot delta R. So it's simply the dot product of these two. 7 minus 2 dot 5 8. 7 times 5 is 35 minus 16. So that's going to be the work done. 35 minus 16. It's going to be 19. It would be in joules. But since this is maths, we don't stress too much about the units. They'll drill you as far as those are concerned in physics or chemistry or whatsoever other applied science course. So for us, that 19 is going to be good enough. One more example. Alright, in this example we want to prove an identity that was stated earlier, that this scalar triple product is equal to this determinant here. So what we need to do here is to work on the left hand side, find whatsoever we find, work on the right hand side, and then show that the two sides are equal. So if we start with left hand side, we're going to start with B cross C. So B cross C is going to be, we're going to have the components of B here, components of C here, so this is going to be I into B2, B3, C2, C3 minus J, B1, B3, C1, C3 plus K, B1, B2, C1, C2. And so this is going to be B2, C3 minus B3, C2. And then from here, if we do this one first, it's going to be B3, C1, C1 minus B1, C3, and then the Z component is going to be B1, C2, B1, C2 minus B2, C1. So that's going to be this cross product here, and then we do a dot product with A. So A dot B cross C. So all that's going to happen is I'm going to multiply this by A1, multiply this by A2, multiply this by A3, and add up. Okay, so So let's start with this one. So it's going to be A1, B2, C3. A1, B2, C3 minus A1, B3, C2, and then plus A2, B3, C1 minus A2, B1, C3, and then finally plus A3, B1, C2 minus A3, B2, C1. Okay, so that's the left hand side. Then we need to work on the right hand side now. So on the right hand side we simply have the the 3 by 3 determinant C3. Yeah, tell you what. So in fact what we can do here, so here if we just factor out A1, so it's B2, C3 minus B3, C2, and then between these two we can factor out A2. It's B3, C1 minus B1, C3. In between these two can factor out A3. It's going to be B1, C2 minus B2, C1. Then if we expand this along the first row, so it's going to be A1 times this determinant, which is B2, C3 minus B3, C2, and then A2 times the determinant of that 2 by 2. It's going to be, so A2 is going to be B3, C1 minus B1, C3, and the last one is A3 times this determinant B1, C2, B1, C2 minus B2, C1. Now you can see that this one is this one here, and the second one is this one there, the third one is that one, and so the left hand side is equal to the right hand side. Hence the proof is complete.